All right, here we are for part 2 of today's lecture, continuing on with our study of objects in rotating reference frames. So now I want to look at plane motion relative to rotating reference frames. Plane motion relative to rotating reference frames. This is a very classic problem in engineering where you need to transform a reciprocating motion into a rotational motion or vice versa. So this is when I say classic, I mean really to the dawn of steam engines and that kind of thing. See, early steam engines, now we have things like steam turbine engines and very advanced forms like that. But the very first steam engines were, simple pistons. They had a series of valves where they could make this thing go up and down. They could make a piston go up and down in its housing. But the problem was that you would have a rod with an up and down motion that was very powerful, a lot of force behind it. But what you needed to do to actually do useful work in most cases was you needed to find a way to transform that into a rotational motion. So I have the up and down motion, and there's a lot of energy behind that. But what I really want is some sort of rotational motion. There's a whole lot of it was very common in early periods of the Industrial Revolution, where nowadays we would not have a dedicated huge, say, steam engine for a factory or something like that. We'll just connect it to the electric grid, or if you're Elon Musk and you don't want to use the electric grid, I guess you can use a bunch of solar panels on the roof, but you're not going to have a great big steam engine in the corner powering the whole thing. Well, that's what they would do in the early 1800s. If you were working at one of the first industries to be, say, industrialized, would be something like the clothing industry and the textile industry. In fact, even today, when a country is undergoing industrialization, the textile industry is always the first industry that moves into town. Driven by cheap labor and things like that. But anyway, in the early Industrial Revolution, it was very common in certain factories in, say, England and then later the US and Germany and other sort of crucibles of the Industrial Revolution, where you would imagine you had a big factory floor and you would have an enormous steam engine at one side or an outbuilding or in the middle of the factory floor even, and then from that was attached to that was a great flywheel, many multi-ton flywheel, and to turn that flywheel, several pistons were connected to it, using mechanisms to translate this horizontal motion of pistons. Again, because they didn't have the metallurgy needed to create something like a steam turbine engine, this was the best they could do, and so. But that wasn't really that useful. You needed something rotational to really do useful work. So this was sort of one of those classic problems in mechanical engineering, and people spent a lot of time, and there's a long history of patents and things like that went into ways to transform this horizontal or this lateral motion or translational motion into a rotational. See, once you have it in rotational, you can do a lot of useful things with it. You can for example, you can use gearing on it once it's rotating. You can change the torque in it. You can change velocity. You can transform between torque and velocity, rotational velocity, just using gearing, right? You can, if I have a rotating shaft, I can try to draw a gear. If I want to make it rotate slower, I can just attach it to a larger gear, right? And for every one rotation of the smaller gear, the larger one will do only half a rotation or a third of a rotation or whatever. And if I wanted and what this does is, this means that this one will go slower, but it will have more torque behind it, right? Because the moment arm from the center is greater. So you can just like you can dial up and down voltage, with mechanical gearing, you can dial up or dial down, trading omega, your rotational velocity, for torque. And but you need to get things rotating before you can do this. So in pre-electric days, the only way to really transmit power usefully through a factory setting would be through rotational motion. And so what you would have is this great big steam engine in the middle of the factory floor and there'd be some mechanism, some sort of collar and rod mechanism to think about the kind of mechanism that's on the side of a steam locomotive, the classic sort of old Western steam locomotive, and it's transferring things back and forth between rotational piston energy or piston motion and rotational energy used to drive the wheels. Well, and then the center of the factory, so you'd have this big steam engine in the middle of the factory floor, and then coming up off of that, once it was, you'd have the big flywheel gathering all the energy up, and then once that was moving, you would have a series of gears, belts, pulleys that would then translate that energy to things like, you might have cutting stations that powered small saws, things like sewing machines, things like looms, any kind of, band saws, whatever kind of material you need to work with that you need power for, mechanical power, you would then, it would be distributed through a large building using just gears and pulleys and clockwork mechanisms, that kind of thing. Maybe not clockwork mechanisms, but think of clockwork mechanisms and gears and pulleys and belts and all those kind of things. That is how power was distributed industrially. It couldn't be distributed long distances, but within the same factory, you just have one great big steam engine in the middle of everything, powering everything else. And so, anyway, and it was the 19th century, so there was probably some poor 8-year-old feeding it coal, but anyway, welcome to the 19th century. So let's go back and talk about, let's go back to this and look at plane motion relative to a rotating reference frame. Sorry, that was a bit of a tangent. Plane motion relative to a rotating reference frame. To a rotating reference frame. All right, so we're going to have a collar P on a rod B, or rod OB. So consider rod OB that I'm going to draw. So O here, and then B. And this thing is going to be rotating with angular velocity omega. Angular velocity omega. And there'll be a collar on this. There will be a collar on this rod that can slide up and down. So this collar can slide up and down as this thing is moving, as this thing is rotating. And I'm going to call this collar A here. And then I could have AC. Let me show some accelerations this thing can have. AC. AC would be R omega squared, or actually 2RU. And we'll see what U is in a moment. 2RU and AA, A sub A, is equal to R omega squared. All right, so what is U? Well, this thing, U is going to be the relative velocity of the collar with respect to the rod. So it's sliding along the rod with velocity U. So U is the relative velocity of collars sliding along rod along the rod along rod OB, I should say. Better rod OB than rod BO, but that's okay. And the rod is going to rotate with constant angular velocity omega, as we said. And position A, the point A on the rod corresponds to the instantaneous position P. point A on the rod corresponds to, as we discussed previously, to instantaneous position P. Position P. Instantaneous position P. Now, the absolute acceleration, this is going to be AP is equal to AA plus A of P with respect to the rotating object, P with respect to F. Remember, I was using fancy F to refer to my rotating object, plus AC. Plus AC. Then, where, and AC is my Coriolis acceleration, AA is going to be equal to omega dot cross R plus omega cross omega cross R. Omega cross R, and or I could simply say AA equals R omega squared, lowercase omega squared, R omega squared, and A of P with respect to F. Well, if P is the position, the fixed position is the position, that's just going to be 0. Or this is equal to R. Let me use the same red rotating reference frame that I used previously. R double dot of OXY. This is equal to 0. And then the centripetal acceleration, AC, is equal to 2 omega, to capital Omega, 2 omega crossed into, and that should be a vector, 2 omega crossed into the velocity of P with respect to F. With respect to F, or simply, in our case, AC equals 2 omega U. 2 omega times U. Okay? And then I can also summarize by saying, summarize by saying the absolute acceleration of the radial and the absolute acceleration consists of the radial and tangential components shown. So we have radial and tangential components. The tangential component is the Coriolis acceleration, and the radial is the AA we mentioned previously.
2 omega U, 2 RU,
Where, right here?
AC.
AC equals 2 omega U, I believe.
No, there's 2 RU.
2 RU.
On the top left on the diagram.
Oh, 2 RU. Oh, sorry about that. Yeah, that's 2 omega U. Sorry. Yeah, that's 2 omega U. Sorry about that. Okay. Next, okay, let us consider this. All right, so let's continue on with a little more theory. So more plane motion relative to a rotating frame. So now let us look at a change in this thing over time. So I'm going to consider both essentially a P and a P prime, or motion along something like this. So consider a system like this, where we had the initial position of the rod and a final position in the rod. So we have the rod's initial position, So we have this initial position here, and then the final position here. So initial and final. And let's say initially the collar was lower and then it became high, then it went to a higher position. So initially the collar was here and then it went up here. And it also got thinner apparently. Here. So let's say initially it had velocity or radial velocity u, and then up here maybe it has u prime. U prime. And then the initial, if I look at some dimensions here, initially it had r, and then later it has a distance from the center, which would be, let's say this is delta r. Delta r. So its final distance from the center will be r plus delta r. Then this here, let's say that if omega is constant, then VA here would be, let's say this here, actually AA, sorry. I believe, let me double check. No, that would just be VA, sorry. Initially I would have VA here of collar A. Let's say this is A and A prime. So here, this would be VA, and this would be VA prime. So we know how to go from centripetal to our linear to our, we know how to go from our rotational velocity omega, our angular velocity omega, to a tangential velocity, and it is done as such. This is our omega we have. Well, we already know that in general, V equals R omega. And so that will hold true here. So VA, or in this case, I can say VA equals R omega, and then VA prime will be equal to R plus delta R times omega. R plus delta R times omega. And then let us say this goes through an angle change of theta, or delta theta. A change in angle of delta theta. Delta theta. Okay. Boy. Okay. Isn't that fun? All right. Okay, so let's figure this out. Let us look at the velocities here. At t, well, v is going to be equal to va plus u. At t plus delta t, v prime is going to be equal to va prime plus u prime. U prime, fairly straightforward. Now, I'm going to set up a few vectors and work with them. So I'm going to set up another diagram of velocity vectors and analyze these. Here, so consider two positions, capital R and capital T. Here, working two velocities, or what you might say. So let's say this is R and R prime, and then T and T prime. R prime and then capital T and capital T prime. Where these are basically the vectors of the two components. So let's say this is here. Actually, let me, no, No, let me not label them like this. Let's say this is u and u prime. And this is going from, and the connecting vector goes then from r to r prime. From r to r prime. And then let's say here we had VA. And VA prime. And VA prime. And VA prime. And let's say it went from essentially, then you have maybe T here. Maybe you have T here to T prime, and then T prime. So T prime and simply T. So T prime is, so T is the vector from the tip of VA to VA prime, and T prime is the remainder of T, or the remainder of the velocity. Okay? All right, so the change in velocity over delta T. So I'm basically interpreting the change in velocities as I'm interpreting velocities as a vector and labeling them as such. Change in vector, or sorry, in velocity over delta T is represented by delta V is equal to RR, line segment RR, or RR prime, plus TT prime, plus, or T double prime, back here. Actually, yes, here, just a second, T prime, yeah. R prime and T prime. Okay. Double prime. And I think this, I should call this point, we're looking at points here, sorry. If I want to look at, I need to relabel this a bit. This should be, just like R and R prime were points, I want to call this point T, this point T prime, and this point T double prime. Sorry about that. Okay. Huh? Oh, go back? Okay. So instead of these being vectors, sorry about that, T, T prime, and T double prime are points, are positions, are coordinates. So we start at T, we go to T prime, then T double prime. Okay. And then, additionally, plus T double prime, T prime. And if I look at these vectors individually, T double prime is due to the change in the direction of the velocity of point A on the rod, is due to the change in direction of the velocity of point A of the rod, of point A on the rod, and then I can say the limit as delta T approaches 0 of this value, T double prime. So again, T double prime is from here to here, all the way along here. So it would be from here to here, cutting out the T in the middle. Or actually, did I mislabel that? Yes, I did. Sorry about that. That's T prime. That's T double prime. I can't make up my mind today. T double prime, T prime. So T double prime is due to the change in direction of velocity of point A on the rod, and the limit of T as T approaches 0 of T double prime over delta T. How many T's can we fit on the page at once? Equals the limit of delta as delta T approaches 0 of VA times delta theta over delta t. Delta theta over delta t equals r omega omega, or r omega squared equals AA. Equals AA. And recall then from earlier, we know that AA is equal to omega dot cross r plus omega cross omega cross r, or AA equals r omega squared. R omega squared. And then, or r omega squared. And we'll continue to work through this. I have a few more comments on this. And so that equals r omega squared. And then if I want to look at RR then, okay, so let's see here. Okay, we're good. And then RR, another note, RR prime, and T prime prime, T double prime T, well, T double prime T prime. Isn't this fun? Result from the combined effects of relative motion of P, of the relative motion of P and the rotation of the rod. Or I could say the limit of, as delta t approaches 0, of r prime over delta t plus t double prime t prime over delta t is equal to the limit as delta t approaches 0 of u. If you work through the math, you'll find it's u delta theta over delta t plus omega delta r over delta t. Delta r over delta t, or this is simply equal to u omega plus omega u, or 2 omega u. 2 omega u, and we also know that AC is equal to 2. We can recall that AC, the Coriolis acceleration, is 2 omega cross the velocity of P with respect to F, or AC is then equal to 2 omega u. 2 omega u. Okay? All right, so let me then move on to some examples. So I think that will conclude for our some of our theory for today, I believe. Yes, that will finish up what I want to cover in terms of theory, but I think I want to work through a few example problems now as time permits. Oh, so much fun. Okay. So consider something like this. Consider a conceptual question. All right, now, let's say this thing has, you walk along a platform. Let's say there's a rotating platform. There is a rotating platform you are walking with a constant velocity with respect to it. Wow, that's really bad even for me. With a constant velocity with respect to it. At the point shown, which I'll draw below, which direction will you experience an acceleration? Will you experience an acceleration? An acceleration. Well, let's see. So I'm going to have a wheel, a big circular wheel, and my x and y are shown here and here. And this thing is going to rotate with constant angular velocity omega. And I'm here walking along with the velocity v. But that is v with respect to the wheel. So in other words, I'm going on, it's almost like I'm on a merry-go-round, and I'm walking along the radius of the merry-go-round, for instance. So my velocity with respect to the merry-go-round is constant, but I'm still rotating as I'm doing this. So maybe I start at the center and I walk outward toward the edge of the wheel, but my motion will be a bit more complex than just that. Okay? So here, let us consider this, and and the choices are, let's just not worry about that. I will say, I'm going to start with my formula for absolute acceleration of a point P, and AP is going to be equal to, well, the full formula is omega dot cross r plus omega cross omega cross r, omega cross r plus 2 omega cross r dot in the OXY, and let me put that in red for the rotating axis so I can try to be consistent. XY plus r double dot OXY, also OXY. All right. Again, where omega is our angular velocity, right? Omega is going to be our angular velocity in the global coordinate system. And so let me start eliminating terms. I can start canceling out some terms. Namely, this is 0. Why is it 0? Any idea? Yes, something is constant. What is constant? The angular velocity. The angular velocity is constant of my rotating reference frame. It's constant. So this term here, it would deal with it describe if it was not constant. Here, well, let's see, there's no dots here, so nothing's changing, so that's okay. We can keep that. And then this term here, however, will also be 0. Why is that? Why is r double dot in my rotating coordinate system 0? R double dot. Exactly. My velocity with respect to the rotating reference frame is constant. Yes, that is why that is 0. So if I was walking out, or if you're walking out and walking faster or starting a run or something like that along the big wheel, you will be accelerating as you go. So you would have a acceleration there. Now, so let us think about this. How would this actually work, though? Well, the accelerations that you would experience would be in, if we work through this, we will actually find that the accelerations occur in the negative x and negative y direction. In the negative x and the negative y direction. Why is that? So we're going to have an acceleration in this direction and an acceleration in this direction. We'll have one acceleration in this direction and an acceleration in this direction. How can that be? Why is that? Let's try to get away from some of the math and think about this at a simpler level. Why might that be? Any ideas? Well,
It's because the wheel's rotating that way, so the accelerator would have to be that.
well, it's sort of like this. It's like, yeah, the rotation of the distance, the direction of the rotation will actually matter. But first, let's consider the negative y one. That's the one that's easier to explain. If this thing is rotating, right, there must be some sort of centripetal acceleration to make me go in a circle, right? And so that centripetal acceleration will point toward the center of the circle, right? And since I am above the center of the circle right now, that acceleration, that centripetal acceleration, has to be pointed in the negative y direction. Okay. However, as I am walking outwards, you would agree that a point here, if I were to do a plot of the velocity, the tangential velocity versus radius, would it not do something like this? Like this v? As you went to a higher and higher radius, your velocity would increase, would it not? Your tangential velocity would increase. So if I'm walking outward like this, I have to be, assuming I'm not like slipping and sliding along the wheel, if I'm being carried along by this wheel, there must be some sort of tangential acceleration that's going to pull me along. Is there not? There must be something that will make me accelerate in that increasing horizontal direction. And that would be a tangential acceleration. And because the wheel is rotating in this direction, in order to gain more velocity in the left direction, I have to have an acceleration in the negative x direction. I simply have to have an acceleration in the negative x direction. All right. Thoughts on this? Lovely, huh? Okay. So I have one more example problem, this one numerical, and I think I'll work through this, and then I will let you go maybe early if we finish early, maybe late if we finish late, we'll see. Okay. Well, hopefully early. We'll try to get through this. It's quite a bit of it. I just want to get your hopes up. And like you paid, actually, wait a minute. Now that I think about this, this numerical example, I think I may post it on the website. I think that might be a bit more effective, or maybe I can post a follow-up video later or something like that. I think we might call it there, unless there are any objections. No? Okay. All right, I think I'm going to call it there. I think that about finishes what I want to cover in Chapter 15. I will post an example to the website, and that will do it. So, all right, thank you as always, and I will see you all on Thursday. Thank you.